Okay. Hello everybody. I am Somnath Hazra, a PhD second year student at IIT Kharagpur, and this is a live third week live interaction program on the course CS100 Operating System Fundamentals, and this is an NPTEL live session. So as you may know, these sessions are recorded, and these sessions will occur every week for the 12 weeks duration of the course, and every week we will pick up the topic that has been taught throughout that week, and we'll discuss some of the questions that were present in the previous year's assignment, and they will be helping you in solving the next assignments, the week's assignment actually. So this week we will be discussing about processes. So yeah, let's start. So let's see the first question then. So a program becomes a process when the program is stored on a disk as an executable. The executable file of the program is loaded into memory. The process replaces the program which was stored on the disk, or none of the above. Would anybody like to contribute to the answer? Please write your answers in the chat box, otherwise it will create errors or noise. So yeah, so this is the first question. So as you may know, the program that is, suppose for example the C program that you write, so it has an extension .c generally. So after you write the C program, you have to compile it, right? So that after you compile it, suppose you are in a Unix operating system, so it will create a suppose you are compiling it using a GCC compiler, so which is the GUNIC compiler. So after you compile it, it will create an a.out file, which is actually an executable file. If you are on a Windows system, it will create an a.exe file, which is also an executable file for the Windows subsystem. So after that, you need to run that process in order to see what is the output of your code that you have written. So how do you run that file is, as sir has taught in the theory sessions. So you can either use the command line, and in a Unix subsystem you can type the /a.out command, and then the output will be displayed in the terminal. Or on a Windows system you can simply type a or a.exe, and it will give the output on the in the command line. And in the Unix in the Windows system, you can use the graphic GUI also, and you can simply double click on the executable file, and that will also show you the output. So anyway, so that is how you get the output of a code. So when the executable file runs, that is when we call the program as a process, right? So so when does that happen actually in this whole scenario, in this whole sequence of actions that takes place? So when do you think that happens? Okay. Any other answers? Anyone else who would like to contribute? getting answers of B. Okay, everybody is saying B, so let's see what is it, what the answer is it is B. So yes, as I said, the executable file, once it is loaded into the main memory of the computer, it becomes a process, and that is when it becomes ready to run. That is, it is loaded into the main memory of the computer, and now it can get access. It is a contender for getting the CPU access, and then it can run. So once it is in the CPU, once it can access the CPU, once the execution starts, then the program actually becomes the process. Actually, once it is loaded into the main memory, the program actually becomes a process. So the executable file simply is also not the process. So once it is loaded into the main memory, and it becomes a contender for CPU execution, so yeah, then it becomes a process. Anyway, let's go on to the next question. So this is also related to the program and process. So yeah, a program is the dash quantity and a process is the dash quantity. Can you say which one is the active quantity and which one is the process, which one is the passive quantity among the program and the process? So the program, as I said, program is something that you type like the C code, and then you have to compile it, and then it becomes and then you generate an executable file. It may be .exe or .out file. Then according to the operating system, you have to give it, you have to allow it, allow the executable file to be loaded into the main memory, and after that only you can see the output of the code that you have written. So which among these two do you think is the active quantity, and which do you think is the passive quantity? So which option according to you is correct? Anyone would like to contribute? Okay, Vishal says B. Let's see what others think. Okay, Swati says A. Okay. Now, once what we mean by active and passive, we are saying these terms with respect to the CPU execution, not from the user perspective, right? So the term active and passive means which is directly getting access to the CPU, which is directly getting doing computations in the processing unit. That part is the active part, and the other, which is just present in the secondary memory, which is not directly getting access to the CPU, that is the passive part. So from the user perspective, you may think that the user gets to directly write the code, write the program, so that may be the active part, but no, actually that is the passive part, because you just write the code, but that code, that file, that C file for example, is not directly present in the RAM of the computer. That file is not directly used for execution. The executable file that is generated, that is used for execution. That is what is loaded into the RAM of the computer or the main memory of the computer, right? So that is what there is where the actual instructions are saved. So that is written, of course, in low level language, as you may know. So C, C++, these are all high level languages. We can understand what is written there, but the computer cannot understand what is written in the C file or the C++ file. So it can understand the executable file. Actually, the computer need not understand. The operating systems need to understand that. As you may have revised it in the previous week's lessons. So we were discussing about what the operating system can understand and cannot understand. So there are various types of instructions that are provided by the operating system that it can understand. So according to that, there is a compiler. The C compiler also varies according to the operating system. So the C compiler that is present in the Unix operating system is different from that that is present in the Windows operating system, right? So anyway, so we are diverting now. So what is the active quantity and what is the passive quantity? Any more contributions? Anyone else would like to answer now? Okay, let's go to the answer now. So yeah, program is actually the passive quantity, as you may have guessed by now. So and process is actually the active quantity, because the process is the part of the code that is actually loaded in the RAM. So that is what is loaded in the RAM, and that is what gives operating systems the instructions, actual instructions that need to be executed, right? So that is what is the active quantity, and the program is the passive quantity, right, from the CPU perspective. Okay, let's go to the next question. So this question is with reference to the process structure. So as you may know, once a process is created in the RAM, there is a structure that is related to the process. And in a Unix operating system, for example, the process structures are stored as a linked list. That is, the previous process has a link to the next process, and so on and so forth. So the processes that are ready, they actually form a queue in the RAM, and what forms a queue is these process structures. So these are actually the things that define all the data and the code segments in the process, right? So this is in reference to the process structure of process structure. So a process structure contains heap that is dynamically allocated at runtime, stack containing temporary data section containing the global variables, or all of the above. So which one do you think is a better suited answer for this question? So what does a process structure contain? So as I said, it defines the process, the whole complete process. It contains the code section and all the data section, all the data that is needed for running that process. So all these are present in the RAM of the process. So what do you think is correct among the following? Anyone would like to contribute? Okay, Shah says A. Nisha says B. Okay, we are getting different answers this time. Let's see. Anyone else would like to contribute? Okay, am I clearly audible? Like, is there a problem with the microphone or something like that? If somebody can just post it in the chat. guess I'm clearly audible, right? So yeah, any more answers? Anyone else would like to contribute? Okay, anyway, let's go to the answer. So actually all the process structure actually contains everything. So as I said, the process is actually stored as a structure in a structured format. So if you have gone through C programming, so you may know about structures that are present in C programming. So yeah, so a process is also similarly stored as a structure. So there is a heap that contains the that is dynamically allocated at runtime. So all the malloc, calloc, realloc, all those function calls, all those calls, the variables that are actually the related variables that are dynamically created through those function calls, they are all stored in the heap, right? So yeah, stack contains the temporary data, for example the data that are created locally in a function. For example, if you have written any C code, so you may know that you can create various functions and you can create local variables in them. In fact, inside a function also, inside a for loop, you can initialize a variable. That becomes a local variable. You do not get access to that outside that for loop. So all those variables, they are stored in the stack, right? And the data section is another section that is present in the process structure, so which actually contains all the global variables. So the global variables, as you may know, they are initialized right at the starting of the program, outside of any of the functions or any of the methods of the code, right? So yeah, the data section is also present in the process structure. So all these are present, and can anyone say, apart from all these three, so what is present? Another thing is present inside the process. So these three define all the data that you need for the code, so for running the code. So what else do you need for running the code? For the process, you have all the data. So now what do you need for running the process? But while multitasking applications, linked list. Is suited, then stack for storing temporary data. Okay. For multitasking, once you talk about multitasking, multi-programming and things like that, those actually refer to multiple active processes. I haven't come to that part yet, but these are with reference to a single process, right? So these all these I am talking about with reference to a single process, not multiple processes, right? So yeah. With reference to a single process, all the temporary data and all the local data that are present in a stack. So you'll understand how. So once you do function calls and once you study about recursive calls in C programming, if you have done, if you have already done, so what happens is, so they those things are actually stored as a stack, right? So once there is a recursion, so you actually stored all the so you actually store all the data in a stack format, right? So all the calls are stored in a stack format, and once the topmost function call ends, then you start popping the stack, start popping from the stack the local data and so on, right? So yeah, that is how the process process structure is maintained, a single process structure. We have not gone into the multitasking and multi-programming parts yet. right? So anyway, coming back to my question, so can anyone say that what else is stored in a process structure apart from all these data storing formats? So apart from all these data, so what else is does the process structure actually contain? So it's the code area, right? Without the code, the process cannot execute. The process does not have any instructions to execute. So what will it do by staying in the CPU? Just by keeping some data. So in fact, for storing the data also you need to write the code, right? So you need to instruct the CPU to initialize a variable with the name A, and then it is an integer type variable which is currently storing the value 5. You have to mention, you have to say all these through with the use of codes, right? By using C codes or something like that. So all those instructions, they are also stored in a separate section in the process structure only, right? So that forms the code section of the process structure. Okay. So apart from all these three sections, there is the code section in the process structure. Anyway, let's go to the next question. So when a process is waiting, these are with reference to various stages that a process can go through, right? State transition diagram, as you may know. Okay. So these questions are with relation to the state transition diagram. Okay. So when a process is waiting to be assigned to the CPU, can you say what state it is actually in? Is it in new state? Is it in running state? Is it in waiting state? Or is it in ready state? So can anyone say? Ready state. Okay. Okay. Ready state. Okay. Anyone else would like to contribute? D. Okay. So everybody is saying ready state. So in new state, actually the process structure is created in the new state once it is in the new state. So actually we can say that it is a state of the process, but there is some ambiguity concerning that. I said that the process is the active entity, so it should be in the main memory of the computer, right? It should be ready to execute. But actually, once a process in the new state resides in the secondary memory, right? So it forms a job queue, as you may know, right? So from the job queue, it comes to the ready state, right, where it actually becomes a process, and it gets a storage space in the RAM, main memory or rather, and then once it can execute, it gets CPU time, it can execute in the CPU, and then it comes to the running state, and if it in between it requires some input output operations, then it moves on to the waiting state, as you may know. So yes, that is waiting, a process that is waiting to be assigned the CPU, it is in ready state. So yeah, you are correct. Anyway, let's move on to the next question. So can you tell the minimum number of states that every process must go through? Yeah. In the state, with reference to the state transition diagram again. So we discussed about 4 states. There is another state, that is the terminate state, right? So once the process is done with the execution, it moves on to the terminate state. Okay, so people are still joining. Vishal says 5. Okay, anyone else would like to contribute? Shailaja says 3. Okay. Okay, anyone else? So as I said, once a process is created, it is a new process, right? So it resides in the secondary memory and is present in the job queue. Then it comes to the ready state where there is a ready queue that is present in the RAM, in the main memory, and that contains the processes that are waiting to be executed in the CPU, right? And then one of the processes, suppose we have a single processor system, so one of the processes will be picked up and they will get the CPU time, okay, and that process can execute in the CPU. And then what happens, yeah, so then what happens is that if it requires IO, if it requires input output, then it will go to the waiting state. Yeah, so after the IO completion, it will go back to the ready state and wait for again the CPU time, and once it gets the CPU time, then it moves on to the it goes on to the running state again, and this cycle continues until and unless the program execution completes, and then it can go to the terminate state. So, but if a process does not require any input output, will it go to the waiting state or block state where it is waiting for the input output operations to complete? No, right? So it need not go to the waiting state. So what happens in what will be the state transition diagram at minimum? So there is a new process that is created, so it goes on to the new state. Then there is the then it moves on to the ready queue where it is in the ready state, right? Then it has the CPU time, okay. So it moves on to the running state then, and after it has completed, it may not require any input output operations. So suppose you are typing a C code where you have given there is no input that is accepted from outside. So so you are just printing 5 or printing hello. In fact, you are not printing anything. You are just opening the main function and then straight away closing the main function. So in that case, what happens is it will go straight away to the terminate state, right? It need not execute anything, it need not wait for anything, right? So what happens is that so what will happen in that case? It goes through 4 states, that is new, ready, then running, and then finally it will terminate, right? So 4 is the correct answer. Okay, and let's move on to the next question. So which among the following statements do you think is correct? That is, a process, this is also with respect to the state transition diagram of the process, okay. So a process can never directly go from running state to the ready state. So I am not talking about transitions through the waiting state or block state. So I am talking about transitions directly from the running state to the ready state, okay. An IO request takes a running process to waiting or block state, okay. CPU bound processes spend more time in CPU, and ready queue shows degree of multi-programming. So which among the following do you think is correct, is or are correct? Anyone would like to contribute? Okay. Just one answer. Just the last statement is correct. There can be multiple corrects also. So you know the difference between CPU and IO bound processes, right? So what happens in case of CPU bound processes is that they spend more time using the CPU, doing processing tasks, right? And what happens with IO bound processes is that they spend more time doing input output operations. Suppose after every statement, in every instruction, you have given an input output statement. You have used a printf statement or a scanf statement. So it will spend more time doing input and output, and less time doing any processing tasks, right? So that is an IO bound process. So once it, as I explained in the previous case also, once there is an IO instructions, what happens is that it moves from the running state to the waiting or block state, where it can do the IO operations, and once it has completed the IO operation, then it can go on to the ready queue. Then it will be assigned again to the ready queue, from where it will be picked up again at some time, depending on various factors which we will study in the coming lectures, that how actually a process can be picked from the ready state to the running state, right? So there are various algorithms for that. So you will study about those in the coming lectures. It is very interesting, those algorithms. There are many numericals related to those algorithms. So you may not know about this, but a process may be preempted. So before starting, before completing the execution, even if there is no input output operations involved, a process may be taken back from the CPU and put back into the ready queue. So that is because maybe a higher priority process has come suddenly. So then it can which has to be immediately taken into account, right? So for example, you have written a code to print something onto the printer, but suddenly the operating system realizes that the printer is disconnected. Suddenly it gets disconnected. So right. So what happens is that it needs to handle that first, then only it can print whatever is the task that is given, right? So so then it cannot continue with the currently running process. So that because a higher priority process has come into the picture, so which needs to be executed immediately. So it needs to go into the running state immediately, right? So yeah. So in that case, a process that is already in the running state, it will okay. So it will go on to the ready state. So yeah, let's see what the answer is. So, yeah, except for A, all the three statements are actually correct. So I have not explained what a ready queue, so what multi-programming is. So in case of multi-programming, so there can be multiple processes that can be loaded into the RAM of the computer, and the CPU will be given to each of the processes in a cyclic manner or on the basis of priority. And there is an algorithm for that. There are various algorithms for that, like which process will be getting the execution of the of the CPU. So depending on that, the processes will be picked up one by one from the ready queue, and they will be executed. But anyway, from the user perspective, it will appear as if all the processes that are present in the ready queue are actually executing, right? So that actually shows the degree of multi-programming, like how many codes, how many processes the CPU can handle at a single time, right? From the user perspective, that is. but internally only a single code is running at a time, right? So yeah, ready queue shows the degree of multi-programming. So so which process will be picked up from the ready queue is determined by a scheduler that is known as short-term scheduler. So short-term scheduler becomes very important because it will depending upon the code that it is picking up, depending upon the process that it is picking up for execution in the CPU, currently in the CPU. So that will determine how the CPU is being utilized. So if it frequently picks up processes which has many IO operations, so the CPU will not be utilized effectively in those cases, right? So so there may be many processes in the ready queue, so it has to effectively use the CPU, and depending upon what process it picks up, the CPU will be utilized effectively. Also there is another scheduler that determines which states will be picked up from the new state to the ready into the ready queue, from the job queue into the ready queue. So that is determined by the long-term scheduler, as we'll come to questions related to that. So the long-term scheduler actually determines that which processes will be picked up from the job queue and put in the main memory, in the ready queue of the main memory, right? So the long-term scheduler needs to pick up a proper mix of CPU bound and IO bound processes. So if only there is CPU bound processes, so then the CPU will be very busy executing tasks, whereas the IO operations, the input output operations will be idle, right? So on the other hand, we cannot let the CPU also to run idle, right? In those cases the CPU will be not used effectively, right? So it has to pick up a proper mix of CPU bound and IO bound processes. So that is what is the job of long term scheduler. So we will come to questions relating to that. Anyway, let's move on to the next question. So which among the following states the process resides in secondary memory? Is it the ready state, is it the waiting or the block state, is it the new state, or is it the running state? So anyone would like to contribute to this? Secondary memory is not RAM, right? Ready state, okay. Sonu says ready, Vishal says new state, okay. Anyone else would like to contribute? Says C, Nisha says C, okay. Anyone else would like to contribute? So a process, as you may know, it primarily has 5 states. It goes through 5 states. So once a new process is created, it is the process resides in the job queue, okay, and then it is waiting for execution, right? So then the long term scheduler sometime after some time it picks up the newly created process that is waiting in the job queue, then it moves on to the ready queue, okay, and once it is in the ready queue, it is ready for CPU getting access to the CPU. So once it gets access to the CPU, it is running. So there is no queue once it is in the running stage, because only one process can execute at a time in the running state. And then suppose it requires some IO operation, the process requires some IO operation, then it moves on to the waiting queue where it can perform all the IO operations that are required. So yeah, and then again once it has completed, once the process has completed the IO operation, it moves back onto the ready state, because it is ready for CPU execution once again, okay. So it moves on to the ready state where it is transferred into the ready queue and again, okay. So as I said in the previous slide also, the new state is the state where the process actually resides in the secondary memory, that is not the RAM, not the primary memory. So yeah, you may again argue that then this is not an active quantity, this is not residing in the primary memory. So actually this is where the ambiguity lies, even though it is a process, so but it still resides in the secondary memory. The process is created, the structure of the process is created, so that is why it is called as a process, but it resides in the secondary memory. So and it is in the new state, so the state of the process is new, is what we call new, okay. Anyway, let's move on to the next question now. So yeah, we had discussed parts of this question previously also. So who controls the degree of multiprogramming? So the degree of multiprogramming is determined by how many processes are present in the ready queue. So who controls that? Can anyone say? Who controls the degree of multiprogramming? The long term scheduler, the short term scheduler, the medium term scheduler, or none of the above? So Nisha says long term scheduler. Sonu also says long term scheduler. Anyone else? Any other answers? Anyone else would like to contribute? Okay, by the way, I forgot to mention that this session is being recorded, since I have to report this session to the NPTEL personnel. So yeah, this session is being recorded, so yeah, just a heads up. Anyway, it will not affect anything from your perspective. Just a heads up. So anyway, coming back to the question. So anyone else would like to contribute? Vishal says C, medium term scheduler. Okay, let me explain what a medium term scheduler is. Actually it's a mid-term scheduler. So apart from the process states that are the 5 states that are shown in the state transition diagram in class in the slides, so apart from there there may be overflow in the queues that are present in the primary memory, right? So for example, a state that a process that is the waiting queue, the processes that are in waiting queue, there may be overflow of the processes that are in waiting queue. In that case, the processes will be swapped onto the secondary memory, so as to free up some of the queue space for some other processes. So what processes will be swapped out to the secondary memory from the waiting queue if the queue becomes if the queue overflows? So that is actually determined by the mid-term scheduler, right? So the long-term scheduler comes into effect after very long intervals of time. That is why long-term scheduler, it determines a long like many processes. It determines which processes will be moved from the job queue to the ready queue. A short-term scheduler determines which process will get the CPU execution time, right? And the medium-term scheduler will be discussing what processes will be swapped out from the waiting queue onto the secondary memory. So it may happen once a process is waiting in the waiting queue also, or it may happen in from the ready queue also. So if there may the overflow of processes, so there may be many processes that are coming into the ready queue. So the ready queue may overflow. In that case, though some of the processes may be swapped out into the secondary memory by the mid-term scheduler. So those decisions are taken by the mid-term scheduler, that what processes will be swapped out and swapped in once there is free space again in the ready queue or in the waiting queue. So yeah. Anyway, the degree of multi-programming is therefore controlled by the long-term scheduler. Okay. So now we come to a match the following question. So match the following this question is with relation to the PCB, process control block. Okay. So memory. So the left side is the information column, and the right side is the relevant process column. So the memory management information. So please, can anyone say which matches with what? The memory management information matches with which of the four options? IO status information matches with which of the four options? Accounting matches with which of the four options? And CPU scheduling information. Like, which among the following is a memory management information, or which among the following is an IO status information? You can just write one relates with what, A, B, C or D, two relates with what, A, B, C or D, and so on and so forth. So anyone will like to contribute? One matches with B. Okay. Chirag says one matches with B. Okay. Anyone else? The memory management information is quite straightforward, as can be seen. That is memory allocated to the process. So yeah. 4 matches with A. Okay. Chirag says CPU scheduling information is related to priorities. Yeah. So which process will be scheduled for execution for the CPU? For CPU execution, the priorities can determine that. So high priority process will get to execute in the CPU fast, right? So 2 to C. Okay, IO status information, list of open files is actually something related to IO status information. Okay. Accounting information, so that leaves us with 3 to D. Okay, so yeah, Chirag has said all the 4. Anyone else would like to contribute? 1 to B, 2 to C, 3 to D, and 4 to A. Okay, let's move on to the answers then. Okay, so yeah, memory management information 1 is related to B, that is memory allocated to the process. IO status information is related to the list of open files that are related to the process. Okay, so the IO status information is related to the list of open files. Accounting information, that is how much of the CPU clock has been elapsed with related to a particular process, that is how much time a CPU a process has spent in the CPU. So that is kept as an accounting information. And CPU scheduling information like priorities and some other things, they determine the CPU scheduling information, that which process will be executing in the CPU next. So those are determined by the priorities, or which process can be swapped out, determine based on which processes are present in the ready queue. Yeah, all are correct. Anyway, next question. So the set of processes waiting for an IO device are called. So where is the set of processes that are waiting for the IO device present? Is it present in the job queue? Is it present in the device queue? Is it present in the ready queue, or none of the above? So waiting for an IO device, it is in the waiting state, right? So once the process is in the ready queue, it is ready for execution, right? None of the above. Think again. So these are the three main queues that are present. So device queue is also known as waiting queue. So since I've written IO device, I've written device queue. Okay, Vishal says device queue. Okay. Anyway, let's move on to the answers. So yeah, device queue is right. So once it is in the waiting state, it is present in the device queue or waiting queue. So where it is where the process waits for the IO operation completion, and then it can move on to the ready state again. That is the ready queue. Okay. Anyway. So let's move on to the next question. So the IO bound processes spend more time doing IO with dash CPU burst, whereas the CPU bound processes spend more time doing computation with dash CPU burst. So what will come in the two blanks? Many short, that is IO for both many short, few very long, many short or few very long, and few very long, and few very long, and many short. So which of the following will come? IO bound processes, they spend more time doing what? Doing IO, but with many short CPU bursts or few very long CPU bursts. And the same with CPU bound processes also. They spend more time doing computation, but with many short CPU bursts or a few very long CPU bursts. That is what you need to determine. So as I was saying, that the long-term scheduler needs to pick up a right mix of the IO bound processes and the CPU bound processes, so that the CPU is not overwhelmed by too many CPU bound processes, and also it is not underused by very less CPU bound processes. So it needs to pick up a right mix from the job queue to put in the ready queue, right? So which among the following do you think is correct? Okay. Anyone would like to contribute? The answer is D. Few very long CPU bursts and many short CPU bursts. Okay. Okay, let's move on to the answer. So yeah, uh, the IO bound processes, they actually spend more time doing the input output operations. So the input output operations take long time. So in that case, they only need a few very less time with the CPU. So they can execute with very many short CPU bursts. So because they do not need too much time with the CPU. Whereas the CPU bound processes, they spend more time doing computation, right? So they need longer CPU time. So they have few very long CPU bursts. So they are not. There is no switching from the from the running state to the. There is less frequent switching from the running states to the waiting or the waiting state. So for the CPU bound processes, so they can execute for long time in the CPU because they have more CPU bound instructions in them. So yeah, in that cases, spend longer CPU time. So with few very long CPU bursts, they can complete their execution. Anyway, let's move on to the next question. So as you may know that what exec system call is used for is you can use the exec system call to execute a different process other than for the child process other than what is present in the parent process. So the code section actually can be so the whole process structure can actually be replaced with the exec system call. Normally what happens with fork system call is that the same code is executed, so there is no copy of the code section that is created, but the other data sections, they are copied into the child process, and then the child process can execute independently, but the code section stays the same and there is no copy of the code section from the parent process, right? But from the PID we can determine actually that if it is a parent process or if it is a child process. So that is written by fork. So fork actually returns the PID of the newly created child process and it returns 0 in case of the child process. So yeah, if so in the if statement it is actually in the parent process, and since the PID is 0 for the child process, so the else statements actually take it in the child process, and you can write different set of instructions. I have written just two different printfs, but you can write a different set of instructions for the parent process and the child process. Suppose you can print hello world in the parent process, and you can add two numbers or multiply two numbers in the child process. So it is doing different set of tasks, right? We can make it do a different set of tasks depending upon whether it is in the parent process or the child process. So but is this equivalent to the exec system call then, where also we can the exec system call can be used to do a different set of tasks in the child process? Can anyone say is it correct or not? Okay, Vishal says yes. Anyone else? No, it is actually not equivalent to the exec system call. What happens is that the same code is present. So in exec the code section is changed, right? So there is a different code that is executing. But what happens in this case is that the same code is present. It is just that depending upon the if statement, we are executing a different set of instructions. That is how the code is designed. But the same code is present in the for both the processes, right? So so this is not actually equivalent to the exec system call. Okay, anyway, so there are two more questions, so for which the answers have been provided, but we have run out of time today. So anyway, I'll close the session for today. Thank you all for joining. So yeah, maybe we'll meet in the next session. So yeah, thank you. Yeah.